Right, we're coming to the central lecture on connectivity. And let me start from scratch. So when I introduced connectivity, I gave you a definition that was really a bit immoral. I said the graph is k-connected if we can't separate any two vertices by taking out fewer than k other vertices. I'm not really allowed to, I shouldn't have been allowed to call that k-connected, maybe k-inseparable or something, right? So I always tell my students when they have to coin new phrases, invent new terms and so on, which they frequently have to do, which we all have to do, not to choose words that name a property of a thing they're inventing rather than the obvious meaning that comes with a word. So we shall see today that the two are really the same. K-inseparability is the same as k-connectedness in the following intuitive sense that, well, if we have a big graph and we call it connected, if from any blob to any other blob we can find a path, right? That was connected. That was fine. So k-connected should mean the obvious thing, right? That we can find k-paths, k-connections. So that's really, when these exist, for all, I'm too enthusiastic today, for all A and B, when there are k-paths between A and B, then the graph is k-connected by the moral definition. That's not the real definition. But it's a theorem, it's Menger's theorem, so we'll prove that today, that this is in fact true. Okay, so I think I'm ready to state Menger's theorem. 1920s or something. He was a topologist for what it was worth at the time. Topology only began to sort of exist around that then. And the usual way to phrase Menger's theorem is by saying that for all graphs A and for all sets of vertices A and B in that graph, and they don't have to be disjoint. I drew them disjoint, but they don't have to be. The maximum number of A-B paths that are disjoint equals the minimum of all A-B separators, the sizes of all A-B separators. So there's a minimum over cardinalities of vertex sets X, sets of vertices in the graph. So X separates A from B in G. And what does it mean that X separates A from B? Well, it means that in G minus X, there is no path from what's left of A to what's left of B. So in particular, if X contains B or A, it separates A from B. Right? That's because A and B are sets of vertices. When we speak of a separator of two vertices, we're not allowing it to contain those two vertices, otherwise it would be too easy. Right? So, but for sets, we do allow that. Okay, so that's Menger's theorem. And it's one of those lovely theorems of which we've had a few by now. So if we do a diagram and note the number of disjoint AB paths we can find, so for fixed A and B, and then we also look at the separators, the AB separators, then it's clear that we can't have more paths than our vertices in the separator because the paths are disjoint, and we'll have to go through that separator. All right, so we have a trivial inequality here, and the theorem says that they overlap, that the maximum of all those equals the minimum of all those. It isn't smaller. And then there exists not only this number, but in fact, if we take any largest set of disjoint AB paths and take any smallest set X that separates A and B, then we'll know something structural about the two. We know that X must consist of exactly one vertex from each of the paths. Right? We are not allowed more separating vertices than we have paths, and we have to hit all the paths in order to separate. So we know not only that these numbers are the same, but in fact we know something structural, that X consists of a choice of one vertex from each of the paths for every largest set of paths and every smallest set of separating set. Okay, and I'm sort of laboring this point a little bit because the structural assertion is really, I would like to say, at the core of it. This is exemplified by when we try to prove Menger's theorem for infinite graphs, then this equality becomes really easy. For finite k but infinite graphs, so when these two are finite, then it's easily reducible to finite graphs. And when these are infinite, then the inequality in fact becomes trivial. You can take any maximal set of disjoint AB paths just by Zorn's lemma or something, maximal in the sense of you can't find another that is disjoint from the ones that you have. And then you notice that the number of vertices they all use all together isn't any bigger than their number. Right? If you have kappa for some infinite cardinal kappa many finite paths, then how many vertices do they use? Well, no more than kappa. So you can take out all those vertices, and you have your separator of only kappa vertices. And you can't bypass that separator because that would be an additional path violating the maximality of that set. So that becomes rather trivial for infinite. But this, the existence of a set of disjoint AB paths, and at the same time of an AB separator that picks one vertex from each of these paths, that's a really, really deep theorem in infinite graph theory. That's perhaps the most difficult theorem that there is. It was conjectured by R.Diestel in the 1960s and proved by R. Roney and Berger decades later. So that's a beautiful theorem for infinite graphs, and for finite graphs, just notice that there's a structural fact hidden in this equality of two numbers. Okay, and then we'll have the usual thing. We'll have certificates, right? So every separator certifies that some collection of disjoint paths that you might have is optimal if it doesn't contain more vertices than you have paths here. not because any bigger set would have to pass through that. So it can't be any bigger because it's a separator. And one of these certifies that this is small as possible, right? Because you need as many as you have paths in here in order to separate. So there are certificates for the optimality of each other. You can also give it this guise of, here's a necessary condition that is obvious and we prove it's also sufficient, or here's a sufficient condition which is obvious and we prove that it's also necessary, depending on how you phrase this. And this obstruction angle, which is sort of related, as we had in the marriage theorem, that you say here's an obstruction to having more paths, namely a small separator. And the theorem tells us that whenever we can't have more paths, there exists such an obstruction. We can't find more paths because somehow they're always entangled. But there's a very simple reason why we can't have more paths, namely that there is a set of only that many vertices that, in fact, separates A from B. So we can't have more paths than that, and that is that it does separate A from B is easy to check. Okay, so it has all these nice properties like König's theorem at the time, which is not a coincidence because König's theorem for bipartite matching is in fact just the bipartite case of this theorem. When you have A and B bipartite graph, what's an AB separator? It's a set of vertices that covers all the edges. Right? If you can't, what's an AB path? It's just an edge. And in order to separate A from B, you need to cover all the edges. And if you do, then you also have separated A from B. So König's theorem is the bipartite version of this. And infinite König, in the structural sense, is nearly as hard, so sort of it's half the proof. It's not substantially easier than the whole thing for infinite. Okay, ready for a false proof? We'll do induction. Induction on the number of vertices on the order of G. So we have our two sets, A and B, and let's give this number a name. Let's call that K. So K really depends on G and A and B. So whenever we have a G and an A and a B in it, and I say K, and I say K, then I mean this minimum here, the smallest size of any AB separator in that graph. And we have to show that we can find as many as K disjoint AB paths. That's the non-trivial inequality. Given K, smallest size of an AB separator, we are able to find a collection, a set of disjoint AB paths, K many. We can't find more obviously, but we can find K. Okay, so let's consider such a smallest separator. Call it X. It has K vertices. Okay. Now, apply induction on the two sides. So, I claim that there is no separator between A and X on this side that is smaller than K. Because if there was, if there was a smaller separator, then this would also separate A from B, because on the way from A to B, you have to go through X, by definition of X. So if on the way to X, you have to go through here, then this can't be a smaller separator. That would contradict the definition of K. Okay, so by induction, there are K paths. And in the same way, we apply induction to this side, and we can find KXB paths, and we just stick them together, and we're done. Any objections? It's trivial. Why is it a theorem? It's pretty, eh? Okay, don't worry. If you can't see anything wrong now, I'm not going to tell you, but you'll find it on your sheet, your exercise sheet. Okay, so there is something wrong with that proof. Just take it as a warning. And as motivation to really look at the definitions all the time of what you're doing. Right. So let me give you a correct proof. So this is the first proof. I'm going to give you two proofs. First proof of Menger's theorem. Given G, A, and B, I have to find K disjoint AB paths. Right. So K, as I told you, is defined as up there. And this time we'll be a little more subtle, and we'll do induction on the number of edges. So let's pick an edge. And let's consider the graph G prime obtained from G by contracting this edge. Then let's try and apply induction and see what happens. So the guiding intuition is as follows. We have A and B, and somewhere we contracted this edge. Right, now we have a smaller graph. Now we can look at a smaller separator, X prime of A and B and G prime. Now I'm saying separator of A and B. This is one of these places where you have to be careful and say, hey, what do you mean? Because we're in the different graph now. The contracted graph has a vertex, V, contracted E. That's a new little vertex, one vertex. And so A and B might not be what they used to be. A and B are sets of vertices of G. Now we have a slightly different vertex set. So we have to say exactly what we mean. Let's call them A prime and B prime to be formally correct, and define A prime as all the vertices that are in A, plus this new vertex if at least one of those two vertices is in A. And the same for B prime. So now that's a formally correct definition of A prime and B prime. And X prime is just some separator in G prime. Right? X didn't exist in G, so we don't have to redefine anything. Right, so now the question is, how many vertices are in X prime? If there were at least K, then by the induction hypothesis, we're in a smaller graph, there are K paths from A prime to X prime and K paths from, by the induction hypothesis, if this is the smallest separator, right, in G prime, if that has at least K vertices, that means by induction there exist K disjoint paths from A prime to B prime. And from those we can easily get K paths in G. So what does a path do when it uses the vertex VE? Well, it sort of somehow gets there, and then it leaves there. And by definition of contracting, getting there means that in G, this edge that is now incident with VE used to be incident with at least one of those two, and the same for this edge. So this path of length 2 from this vertex to VE and on to that vertex in G prime gives rise to a path in G that just does that. And similarly, if this edge was here, and so on. Right? So from these paths in G prime, we get paths in G. They're still disjoint. There are as many as before. So we're done if X prime has at least K vertices. Okay. Now, obviously, you'll have to look at exactly how this path argument of the sort of retrieving paths for G from the paths in G prime, how exactly that works when VE lies in B prime, or when it lies in A prime, or when it lies in X prime, or something. No, X prime doesn't feature, so we just have those paths. So do look at the definitions. I'm not hiding a mistake here, but it's something one has to do properly, yes? Yes. The new vertex can lie in both. Yeah. So in that case, it is a trivial path from A prime to B prime. Does it give rise to a path in G? Yes, it does. It's just one edge. Right? Yeah. Okay. Right, so there are fewer than K vertices in our separator. And why is that not a separator in G? Well, that would give us a contradiction to the definition of K. Well, the only way it can fail to be a separator, an AB separator in G, is that VE lies there. It's one of those vertices. This is another of those statements. The only way, blah, 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 blah. That needs checking, but it's true. So then, so this is one vertex in G prime. So I'll make it yellow. It's one vertex in G prime. So in G, we have a separator X. Of exactly k vertices. Right, just take those two. Again, needs checking that this expanded set is really an AB separator in G. Yeah, so what? Now we're sort of stuck a little bit. So far, what have been the ideas? Answer, none. We just pushed ahead, right? We said, okay, we want to do induction. Yes, okay, let's try induction on the number of edges, which is always a bit more subtle than induction on the number of vertices, because if you delete a vertex, unless it's isolated, you've also deleted an edge. So if you're smaller by the vertex count, you're definitely also smaller by the edge count. But the converse is not true. So you can delete an edge and not get fewer vertices. So this is a little subtle, more subtle than induction by the number of vertices. Okay, so we just pushed ahead with this idea of contracting an edge and got out of it as much as we could, and this is what we got out of it. We know a little more about G now, namely that it has, what do we know about G that we didn't know before? We already knew that G had an AB separator of exactly k vertices. That was the definition of K. What do we know? What's the new? Well, there's one thing new, and that is that two of those vertices have an edge. That's the only new information that we've gained. But that's nice, because now we can say, okay, let's delete that edge. And consider G double prime as G minus E. Okay? And now, okay, we're back in a smaller graph. In this smaller graph, we can't have a smaller separator of fewer than k vertices from A prime to B prime, or can we? Well, let's do the bit that we did there. All right, so let's show that we can't have fewer than k vertices separating A from X in G, because that smaller separator would contradict the definition of K. And therefore here too. So by induction on this side here, which is sort of overkill, it's smaller twice, right? By vertex count and by edge count, but never mind. So we get these paths and we get those paths, and we stick them together and we have k paths. Okay. So, of course, I pretty much said the same as I did up there. So if that was incorrect, why isn't this incorrect? It isn't, but that's just because I glossed over the incorrect bit. Let me not spoil the fun, so you find out what was incorrect up there. but this is, to the best of my knowledge, this is correct. But it does need checking. So, for example, when I said, let's stick the paths together, one really ought to use the definition of path. Right? So what if we use one of these paths from A to X, and suddenly we find ourselves here? Is that possible? Right? So one has to check whether what the picture suggests is in fact possible on the basis of just the definitions of the terms that I'm using, such as paths and what concatenating paths means, and so on. So graph theory always looks so simple, or often looks so simple, and the devil's in the detail sometimes. So one has to check. So another little detail, for example, I told you the definition of A prime and B prime earlier, and I said that we put the contracted vertex VE in such a set if at least one of the two vertices of the edge we contracted lay in that set in G. Did I ever use that definition? Okay, if not, what if I change it? If I say, okay, we put it in A if both these vertices were in A, and similarly for B. So these are sort of sanity checks. There may someday be a mechanical way of verifying proofs. We're sort of making big strides towards that. But for the time being, in my first lecture in the first term for new students, I always ask them, what do you think in mathematics, the most rigorous queen of all science kind of discipline, what is a proof? And they'll think of something grand, quite rightly. Everything we do is grand. However, the definition of a proof, my definition of a proof is rather less grand. It's sort of something like a proof is when, good start, a proof is when sufficiently many, sufficiently well-trained mathematicians have thought about this for sufficiently long, and after considering it, came back and said, can't see anything wrong with it. That's my definition of proof, rather than can be deduced to the axioms in this or that way, and so on, right? I mean, that of course is the formal definition of proof, but one needs to do proper logic to set this up, and so on. And in practice, what happens is my definition. And here, coming up with one of these possible faults, if they exist, like there. How do you do that? You try really hard, try and make everything precise, and then maybe you're fortunate enough that you stumble over something that was overlooked. Maybe you're less fortunate. So there's no guarantee that you can find a hole, but the whole training that I'm trying to contribute to, that you're receiving here, should put you in a position where at least you can say, no, I am now sure. I've sort of checked this, and I really am sure that I've checked all the details and all the definitions and so on. And there's another strange thing in mathematics. It very, very, very rarely, if ever, happens that there are two of these mathematicians from my earlier definition that come back and say different things. Sort of there exists something like a threshold that you pass, and then you say, yeah, now I know. It's not reliable. I've had a counterexample myself when I woke up after thinking that I sort of worked through the details of a really difficult proof I was chasing in the middle of the night, and I went to my desk and I wrote it all down. I mean, just the details so that I'd know in the morning. I was really happy. I slept until midday, and I had breakfast and leisure, and knowing the proof was there on my desk. And I went back to the proof, and it was all just complete nonsense. So it didn't even make sense. I mean, there were no statements there. There was some wild, dreamy kind of things. So the reason I'm telling you that is that I had this by then familiar feeling of, yeah, now I really know. And I had that in my delirium in the sleep. And it outlasted my walk to the desk and back to bed and so on. So you can have this, you can be sure that you have a proof without this being the case, but it doesn't usually last. So strangely and magically, wonderfully, mathematicians do seem to agree. We don't have battles of schools of what are the right arguments and so on, but there's no mechanical way. There's just this, with enough training, which you're getting, think about it for long enough, and then say, you will find that you'll be saying, yeah, that's it. So where does this get me? Yeah, so there are sanity checks, like, I never used this bit of the definition. That can't be right. Or, well, maybe it is right, but then I'll change the definition a little bit, and you'll easily find a counterexample when you change the definition of when does this vertex belong to A or B prime, and play with it, you will find a counterexample very soon. And then you can say, oh, yeah, I must have used it somewhere, and then go back to the proof and find that place. Okay. Right, questions? Good. Oh, one more thing. Another sanity check. It does appear that we've proved something rather stronger. Namely, that in any graph, we can pick an arbitrary edge, and then one of the following two things will be true. Either if I contract that edge, or if I delete it, will my k, for those given A and B, remain the same. That's how the proof, what the proof did, right? So we had G, and we had A and B, and then we picked any edge. Usually, this is where we can be clever. Find an edge such that this and this and this and that is minimal and that is maximal and whatever. So we just picked any edge. And then we said, OK, let's contract and see what happens. And if contracting it doesn't reduce k, then we said, OK, in that case, by induction, we're done. Right? We find those k paths because we're in a smaller graph. And k wasn't reduced. So we get k path for our k, for G. And if it did go down, then we said, oh, but we can delete it. And now we can find our k paths, and k didn't go down. So we seem to have proved that in an arbitrary graph given A and B, you can either pick any edge. You can either contract it or delete it, and k will stay the same in one of the two. So the thing to do now is to find an obvious counterexample to that, and then find the error in the proof, or find why we didn't in fact prove that. Or else, maybe we did in fact prove that, then it should be harder to find a counterexample. Okay, have fun with the exercises. Second proof. Questions about it before I wipe it? No. Okay, proof number 2. Again, we'll be doing induction. But we'll have to see on what. So let me give you a definition first, and that is sort of the starting idea for this proof. This proof does have a starting idea. Let's let's consider any set of disjoint AB paths. And we'll say that another set of AB paths, Q, extends P. I'm not going to write it down. It's all in the book, so let me just say it. Q extends P if it has more paths, uses the same vertices in A as starting vertices, uses the same vertices in B as starting vertices, and at least one more pair because it has more paths. Okay, so once more. Given any set of disjoint AB paths, maybe none, maybe 1, maybe K. Another set of disjoint AB paths extends that if it uses the same vertices in A, the same vertices in B as ends of these paths, and obviously one more. Right, that. So Q extends P. And the idea now is to prove that if P isn't as big as we want, we'll show if P has fewer than K paths, then there is a Q extending P. Yeah, fair enough. This extending is a much stronger property than we really need. All we need is a bigger set to get a contradiction. Right? If we have a set of disjoint AB paths of smaller cardinality than we want K paths, then there exists a bigger set. That's all we need to prove. And in fact, we'll prove that there is a very special bigger set, one that reuses the n vertices of the existing paths in P in A and B. Okay, so start of proof. Let's look at the last vertices of P in B. There are fewer than K, 1 for every vertex in P. And the assumption is that P has fewer than K vertices, right? Paths. Okay, then that means that there exists a path that avoids this, a path from A to B that avoids this potential separator. So that somehow arrives in B without this separator, and it starts somewhere in A, maybe at an existing vertex on some P, maybe on a fresh vertex, I don't know. Okay, so such a path exists. I want to call that R. Right, now if R doesn't hit our path system curly P, we can just add it. And then we have extended curly P. So it does hit, and let's consider the last vertex on R, last vertex on R, or of R, on the vertex set of all these paths together. This last vertex isn't in B, right? Because this path R gets to B minus the vertices that P has in B. So if it does hit a vertex of P, it's somewhere outside B. Okay, and now comes the clever bit. Now, the idea is to apply induction by making B bigger, or, if you like, induction on the number of vertices not in B. So our new B, that's not so easy to see, huh? So our new B is the old B, plus the bit of path from X to B in curly P. So X lies on some path in curly P, so we can follow it to B on that path. And there's at least one edge, so X isn't already in B, as I pointed out earlier. So we'll include this entire path here in B to form B prime, and we'll also include this last little bit of R after X. Why? Well, I can't say why without showing you the proof, so I will show you the proof. Now we can apply induction with this larger B prime, because our induction parameter has gone down, the number of vertices not in B. Or, if you like, the number of vertices on any path in curly P, that's also gone down, right? Because we have the same paths in curly P as before, and this one here hits a little earlier. These here are not in curly P paths by choice of X. These here are, but they're only on one path. So we have P prime that consists of the other paths in P, curly P, plus this one that has X on it, and there we stop at X. And that's our P prime. Okay, now we, by induction, this P prime extends to some Q prime. What does extend mean? It means there's, there's a path system that reuses the vertices of P prime in A, and it reuses those in B prime. Those are the ones of P in B plus this little x. That reuses those. and contains something else, contains at least one more path. So all these get used, maybe along R, maybe not, doesn't matter. Somehow these all get used. These all get used. That not necessarily, but X gets used. So we somehow go into X. And then we somehow arrive at an additional vertex in B prime that we didn't arrive at before. So that could be here, or it could be something there. Or right, our curly prime contains a path that is not in Q prime, is not in Q. Sorry, that is not in P prime. And in fact doesn't use an end vertex of the paths in P prime. Sorry, that's what I want to say. Doesn't use one of those end vertices because they already got used by some other paths in Q prime, but Q prime is bigger than P prime. So it reuses all the vertices of P prime in A and B prime, and it has one more path. So this one more path can start somewhere here, maybe at a fresh vertex. We don't know. It might be this one here, right? That somehow arrives down there. We don't know. And maybe there will be a fresh one. But this might arrive there. Okay, but we're only looking now at where this additional path here ends. And if it ends here on R in B prime, then we can find a bigger system for G. Namely, we'll just reuse Q prime for all the paths that connect vertices that are also end vertices of P. And then there's this additional path that lands here when it hits B prime. And we take that, go home to B, and the path that ends at X, we continue to be here along the original path from curly P that X was on. Right? This is not used now because that's all in B prime. That's the reason why we put it in, well, one reason we put it in B prime, right? So the new paths stop as soon as they hit B prime. So the path that ends at X, and there is one, because we're extending curly P prime, which does have a path ending in X. So this path here can now be extended to the original B along that path and is disjoint from this. Fine, so we've found K paths in G, and the alternative is that this new path here hits B prime there, but then this incoming path is rerouted there, and this one is rerouted there. So we get a bigger path set also for the original B. And that's that proof. Questions about it? Okay, so yeah, I thought it's a clever proof. It sort of has something unexpected to it, to the observation that it's not clear which idea comes first, that of extending B or that of defining this extension They sort of come together. And that's often the way in which things are clever, the two ideas that are both not obviously useful somehow make sense together and are eminently useful together, but how do you find them? How do you pair them up? So, yeah. Okay, so how are we doing for time? Good. If there are no questions, then I'll give you some corollaries. There's also there's a third proof in the book, which is more natural than this. It's also a little more pedestrian. It's not as short as that, and it has this quality that it extends to sort of ultimately to infinite graphs. So for countable graphs, the proof is in the book. For uncountable graphs, it's much, much more difficult. For countable graphs, it's not so difficult. It's like 3 or 4 pages. And we do that in the infinite graph theory lecture course, not here. And the third finite proof sort of prepares the ground for that, which is why I cover it there rather than here. Okay, so corollaries. A fan is a set of paths from one vertex. Let's all start at one vertex and are otherwise disjoint. It's a subdivided star. That's called a fan, right? And you Menger's theorem tells you when you have an A to B fan, where B is a set of vertices and A is one vertex, of strength at least K. And the answer is if there is no set X of vertices that separates little a from big B, where this set of vertices is not allowed to include A, but is allowed to intersect B. Right? And how does one prove that? Well, the same. It's really a corollary. So you look at the neighbors of A, and you call that set of neighbors all of them now. All neighbors. We don't have these paths yet. Right? And then you apply Menger between this A and this B, and it tells you that you get K disjoint big A, big B paths, if and only if there's no such separator. The separators are precisely the ones we're considering now, that separate little a from big B without it being allowed to include little a. And a set of disjoint big A, big B paths extends to a little a, big B fan, clearly, and every fan from little a to B gives rise to a set of disjoint paths from the neighbors of A to B. Right? So that's all easy. That's the fan version of Menger's theorem. And you can do that on the other side as well. So if you have a little b, and you can ask how many independent paths, A-B paths, you can find. So two paths are independent if they don't have inner vertices that are the same. So if no inner vertex of any of these paths meets any of the other paths, neither in an inner vertex nor in A or B. Okay, and the answer is pretty much the same. We consider n of B, call that big B. And then we apply Menger between A and B. Now there's one little caveat, and that is that it works only if AB is not an edge of G. Right? If there's an edge from A to B, then that is already an AB path, and it isn't reflected in this translation of that theorem to disjoint paths between the neighbors of A and the neighbors of B. These neighborhoods may well intersect. They may be identical. Right? Okay, so that's an easy corollary for A and B, non-adjacent. So once more, what does the corollary say? It says that for every graph G and for every choice of distinct vertices little a and little b that are not adjacent, the maximum number of independent AB paths equals the smallest size of an AB separator. No, separator are not allowed to include A and B. Okay, so those are two corollaries. Then there's edge Menger. Sorry, I keep saying Menger in English, but it's really Menger, right? Sorry. What does that say? It says that, well, you can have it for sets, you can have it for little vertices. Let's phrase it for little vertices, little a and little b. The maximum number of edge disjoint AB paths equals the smallest size of an edge separator that separates A, or a set of edges that separates A from B. How does one prove that? Well, you can do the same, something like the same. We'll also get an independent proof later in this lecture. But you can also do a trick. And that is to apply Menger to something called the line graph of your given graph. So what's the line graph? The word line does not come from geometry. It means edge. So I think I've mentioned Harari before. So Harari was one of the early people in graph theory. He wrote the first, I think, English language book on graph theory in the 1960s. And he didn't say vertices and edges, he said points and lines. And this hasn't really stuck except for line graph. So a line graph is a graph on the edge set of the given graph. So the vertices of this line graph are the edges of your graph, and adjacency is the same. So two of those edges are adjacent as vertices of the line graph whenever they're adjacent as edges in the original graph. So if the original graph has, like, these edges, right, somewhere, then the line graph, these are adjacent. These three edges are adjacent. So these vertices are adjacent in the line graph. These vertices are adjacent in the line graph, all of them. Yeah. So the line graph has literal complete graphs for every vertex of the original graph. These complete graphs overlap in edges of the original graph between such two original vertices. Okay, and you get edge Menger by applying vertex Menger to the line graph. Easy exercise, not worth following up really now, but just check it. Yeah. So there's now something, these are sort of things that you look up when you need them, not really worth remembering, but they're so easy to remember that you can't help remembering them probably. So there's also something like a global version of Menger's theorem. And that is maybe the most important, well, not most important, but it's one of the most applied versions. And it says that a graph G is k-connected for any given k, if and only if no two vertices of the graph can be separated by fewer than k vertices. Sorry, that's the definition of k-connected. Right, so that's so I want the moral definition now, which isn't the real definition. So G is k-connected if every two vertices can be joined by k independent paths. All right, so every two vertices hang together k-fold. Right, now notice that this is not an assertion about a pair of vertices or about a pair of vertex sets or something. It's an assertion about a graph. So the whole graph G, given some natural number k, is k-connected. If no two vertices, that's the definition now, if no two vertices can be separated by fewer than k other vertices. And the theorem says it's k-connected if and only if we can join every two vertices by k independent paths. Now, if we can do that, then clearly it has to be k-connected, and there's an edge version as well, so k edge connected then these become edge disjoint paths. And here it's the same. If you have k edge disjoint paths between any two vertices, then you can't separate any two vertices by fewer than k edges. Then the graph is k edge connected. The forward implication is also clear for the edge case. If you're k edge connected, then indeed any two vertices can be joined by k edge disjoint paths, and that is just edge Menger. Now, for vertex separation, this nearly works. So if G is k-connected, is it true that every two vertices can be joined by k-independent paths? Well, we improved that, didn't we? Yeah, we proved it, except we had to make this silly assumption here that A and B are non-adjacent. So if G is k-connected, then every two non-adjacent vertices can be joined by k-independent paths. That much we know from here. But, I mean, yeah, if they're adjacent, that should help, because that gives us one path. So, proof. Consider the graph without the edge. Right, so we want to prove that every two vertices are joined by k independent paths, even if they're adjacent. So let's consider two adjacent vertices, call them A and B. And now we just delete that one edge. That's an edge. AB is an edge. Okay. So in G prime, it will be enough to find k minus 1 paths, because then AB is another path. We're not looking for disjoint paths, just independent. So the one edge path AB is independent of all other AB paths. So yeah, we only need k minus 1 paths, so that really should be easy. If not, then we have a separator between A and B of size at most k minus 2. Surely that can't be the case. I've deleted the edge AB, so we don't have an obvious contradiction, but all we need for a contradiction is one more vertex. So let's look at one more vertex that is either left or right, not one of those. And then we have a contradiction, because now A is not adjacent to this little v, and they're separated by even 2 fewer edges than are allowed. Or if that vertex is here, then it's separated from B by 2 fewer vertices. So the only little quirk that might come up is, are we sure such a vertex exists? Is there another vertex that is not in the separator, is not A or B? Yes, because we're assuming that G is k-connected. Unfortunately, 100 years ago, we defined k-connected to mean no two vertices can be separated by fewer than k other vertices, and G has at least k plus 1 vertices. Ah, brilliant. So there's k minus 2, k minus 1, k vertices, but it has at least k minus 1, k plus 1, so there's one more. I was lucky. Otherwise, right, think of Socrates. Otherwise, we would have gone back and changed the definition of k-connected, perhaps, and required k plus 2 vertices. Well, don't know. Okay, so that's it for Menger's theorem. Remember this global version as well as the original version up there, and all the others somehow follow easily from these. Questions about connectivity? Okay, now I'll move on to do something quite different for the sole reason that it implies a new proof of, very easily, of edge Menger. One can also, with a little bit of trickery, deduce vertex Menger from the theorem I'm going to show you. But edge Menger is really instant. So this is about network flows. We want to model, that's how network flows sort of were born, as an attempt to model flows in real networks. So you have water pipes, and they're metered big sort of nodes where the water flows in from all sides and flows away through some other pipes. Or you have electric flows through wires that have some nodes where they all meet. You might have data flowing through some network and some hubs between them, and so on. So there's a theory of network flows that models all these things. And before I tell you the basic definitions, just one word about how modeling has its place in mathematics. So modeling happens when we want to explain something in the real world using mathematics. Now, the two are sort of not very friendly to each other from the outset, because mathematics is something that we invent out of thin air. Right? We come up with axioms of set theory based on logic, and we create mathematics without regard to the world. And the world, and the mathematics that we create has all sorts of, satisfies all sorts of quality criteria that I keep rambling about occasionally, but being instantly applicable is not one of them. You can ask for mathematics to be applicable, and that certainly is some nice property, but it takes a few steps, because as such, a mathematical theorem has nothing to do with the world. We have to make it have something to do with the world, and this something is called a model. So the model of a network is going to be a graph, something like this, where we think of these edges as the wires in the electrical network, or the data lines in the data network, or the pipes in the water network, and so on, and these vertices as nodes in that network. But when we prove things about the model, i.e. about this graph, for example, how much flow we can send from S to T, and I'll have to define, in order for that sentence to make sense, I'll have to define what a flow is, and I've defined how we measure how large that flow is, and so on. And all these definitions will be mathematical definitions. So, for example, a flow is a map from the orientations of the edges to the real numbers. What is this set E arrows? The definition of that is the set of oriented edges which are in turn defined as the ordered pairs for the unordered pairs of vertices that are edges. Edges are two sets. Two sets has two pairs, and we call those pairs the orientations of this edge. And a flow maps every oriented edge to some real number, and we think of that as the amount of whatever that goes through this edge in this direction. It's important, we're not talking about a directed graph, we're talking about an undirected graph with oriented edges. Yeah, but then, I mean, what's the maximum value of this flow? We'll get to that problem, how to define that, but for now, these values could be anything. It could be really, really big. So we also want a capacity function. So that's a function that also assigns to every oriented edge some positive real number, and let's make it a natural number, an integer, to simplify things. We also get some stronger results, since we only have finitely many arguments anyway. That doesn't restrict or reduce our generality at all. Right, now we have a bit more of a model already. So we want, F to satisfy certain things, and one of the things, which I'm calling F3, is that F doesn't exceed C. So the flow through an oriented edge isn't allowed to be bigger than the capacity that we've already assigned to that edge. So this edge may have capacity 5 in that direction, capacity 3 in that direction. That's fine. Flow, not really. F of xy should be the negative of f of yx, which is just really for convenience. When we have a water pipe in mind, either water flows from here to there or from there to there. So we could say only one of the two is defined. Either only xy ordered pair has a value under f, or yx has a value under f. But it's much easier to say, well, if water flows from x to y, then this has some positive, or it has some value. And then we just define the inverse flow along that edge as the negative of that. We can do that. And yeah. And then here's the only interesting requirement, that at every node, we somehow want the amount of flow in to equal the amount of flow out, except for S and T. So if we think of S as a tap, or S for source, and T as a sink for terminal. And so water is allowed to dissipate there and to disappear at T and to originate from S. So, or more generally, at S and T, we make no requirements at all. So for every V not in S and T, we want that the same amount of flow goes in as goes out. And by our convention here of F1, there's a very easy way to phrase that. And that is simply that for all edges VW, the sum of the flow values from V, this V, to the W, over all the neighbors W, is 0. Huh? And usually when you look at network books in computer science, they usually have something like flow in equals flow out, and then they have to consider all edge orientations and so on. It's a little complicated. And with this setup, it's very easy. You just have 0 everywhere, except at S and T. Okay, so now this is a mathematical object. Is it applicable to the real world? Goodness knows. So the real world strikes back and say, okay, you come with all these models, and then maybe in the real world there's something that the model ought to cover and doesn't cover. So what do the people that do care about the real world do, like physicists and data scientists and so on? well, they come back to us and say, please change your model, or explain what we have found here, or whatever. But it's important that this is, the two are separate. So we have our mathematics that lives in its own world, and we can extend it, we can come up with new definitions, prove other things about the new definitions. But we're always in the Socrates environment. And then the real world is a different environment, and what do? They make theories. What's a theory? A theory is a collection of statements of what is going to happen. Predictions. A theory is something like a body of statements that predict how the world is going to, what's going to happen in the world, and can these theories be proved? No. A theory is they can be corroborated. So you make an observation and you say, yeah, that's exactly what my theory predicted. Fine, you're happy. Have you proved your theory? No, you haven't. You make another observation, and in 1,000 years, maybe you'll find something that contradicts your theory. As long as it doesn't happen, your theory becomes sort of more and more accepted, and then at some point, maybe you'll find something that contradicts your theory, and then you have to change the theory. So can an experiment falsify the theory? I said it can't prove it. Can it disprove it? Yes, absolutely. And when is a theory a good theory? I can think of two criteria. One is if it's eminently falsifiable from the outset. So if it gives the world lots and lots of opportunities to come up with data that contradicts the theory. Think of the theory as being sort of self-confident, saying, I can predict lots of things, and I give you lots of possibilities to contradict me, and you'll see you can't. And then the world sort of struggles and tries to falsify that, and if it can't, then the theory gets corroborated more and more, and the more predictions sort of in principle falsifiable predictions it makes, the better the theory. So what's a bad theory? There's things like self-repairing theories that that say things, and when some evidence comes up that seems to contradict, and they have ways of saying, oh yeah, but that's because we built that possibility into the theory already. And so it depends a little on where you are in the sciences. Of course, the harder the facts that the more measurable your things are, the more data-based your science is, the easier is it to come up with good theories in their sense of being easily falsifiable. If you're a psychologist, it's rather more difficult. And so I remember one theory, it's 100 years old or more in psychology, that said something like, what's the reason for all these people taking their own lives? And it came up with the answer. It's the urge to kill yourself. Brilliant. Right? So, yeah, I'm not doing them justice. There's probably a lot more to it. But there has been, in the last half century, an increased momentum in making theories also in the social sciences more quantitative and empirical in that way. There's another criterion that I could think of just now for a good theory, and that is simplicity. That is actually very like mathematics, where we also like to have simple theories. Theory in mathematics means something else, right? But the idea is the same, that you make few assumptions, and a lot follows from these few assumptions. And that's what we're trying to get. Okay, so enough philosophy. That was about half this lecture. Can I spend 5 more minutes proving the theorem? Thank you. So the theorem says that's the max flow min cut theorem. In every network, which consists of a graph and a choice of S and a choice of T and a capacity function, the largest amount of flow, and I have to tell you what that is just now in a moment, equals the smallest capacity of an ST cut. What's an ST cut? It's what you think it is. It's a bipartition of the vertex set into one set called S that contains little s, and then its complement that contains little t. And what's the capacity of this? It's also, again, what you think. You sum up over all the values on the C of the edges from S to S bar. This direction. That's the capacity of a cut. And of course, every flow, an assignment to the oriented edges of some numbers, has to remain below the capacity on every single edge, and therefore also the sum of flow values from left to right for every such cut also has to be at most the capacity of that cut. Now, what does that have to do with this? That's the value of the flow. How much flow goes from left to right? Well, the obvious definition would be take a cut and sum over all the flow values from left to right. There's a slight snag. The snag is which cut? Now, fortunately, it doesn't matter. There's a proposition early in chapter 6.1 that says for all these cuts, the value of a flow, once you have a flow satisfying this, is going to be the same, the sum of all the values from left to right. And that's easily proved by induction. You start with this cut, little s against everything else, and then you sort of incorporate one more, and so on. So, sorry, real induction works. You start with some s and you reduce it. And the reason that induction works is that at this node here, or at whichever node you're deleting, you have as much in as out. So if it was true before, then it's also going to be true if you incorporate that. So that's the pedestrian proof. There's a slick proof in the proof in the notes in the book, which you can also read up. So that's now this is well defined, and how do you prove that theorem? Well, it's one of those theorems again with this vertical line and the max and the min meeting in the middle. You have certificates and so on, all these things. And a trivial inequality that this max is always at most that min. And we want to prove the converse. So we want to prove that we can find this little dot where the two curly brackets meet. We can find one flow and one cut such that the value of that flow equals the capacity of that cut. It has to be at most that, and if we want to prove equality, then it's enough to find one such pair. Yeah, and that's easy. So we have little s, and we have little t, and then we start with the zero flow. Every edge gets 0. And then we look whether we can find a path from S to T such that on every edge in this direction, in the direction of that path, the flow value is strictly less than the capacity of every edge. If we can find such a path, we increase the flow along each of these edges by 1. And we're starting with an integer flow, 0 everywhere. And if we add 1 to all these edges, then we'll get another integer flow. So the flow values are going to go up every time we do this by an amount of at least 1. Right? Consider your favorite cut here. This path goes through there, so that adds 1. Maybe it goes back and forth a few times, right? But it goes forth once more than it goes back. So we get an increase of at least 1. So this cannot go on forever. And when it stops, what do we have? Well, I claim that we have found S. So when it stops, we can't get from S to T by such a path. But maybe we can get to some vertices on a path where we can, along that path, increase the flow values. Let's call S the set of all those vertices that we can get to by increasing the flow there. Then on all edges across the cut from S to S bar, the flow value will be equal to the capacity in this direction. Why? If it wasn't, if this flow value just here was smaller than the capacity here, we could reach that vertex too by a path where we can increase the flow. That would contradict our definition of S. So for every edge from S to S bar, we have the flow value equal the capacity of that edge. So the two are indeed the same. Yeah. Okay, questions? No? Okay, thank you very much.